SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be studying how you can modify the steady-state behavior of the system. Here you're going to find some standard specification which will be function of a reference input and open loop transfer function. So based on the order of the open loop transfer function, we can choose suitably the reference input and we can tackle the steady-state behavior of the system. Then we'll have some example on aircraft system, how we can choose suitably the reference input to reduce the steady state error of the system. Then we'll conclude the lecture. In this lecture, we'll be discussing how we can comment on the stability of the system. By looking at the system transfer function, how we can comment on it that system is stable or not. Let me remind some of the stuff we have done in the last lecture. So we had summing point and we can design the control based on the mission objective, GC of S, and this is our plant, GP of S, the output from the plant, Y of S, and step response, R of S, and this is the feedback loop, unity feedback, minus plus. So here we can design the control algorithm for the system, linear system, and we can fulfill whether the system can track the ideal response, which is Y of S, R of S equal to omega n square plus S square plus 2 zeta omega ns plus omega n square. So this is basically a standard system, second order system. And our main objective is we have to design the control algorithm here for this particular system, which will follow this ideal response. Now, before you design the control algorithm here on GC of S, how we can comment on the plant, whether the plant is stable or not, whether it's stable or whether it is all the poles are on the left hand side or right hand side, or any of the poles lies on left or right. So based on the location of the poles of the transfer function, we can comment on the stability. Let me draw S plane. This is the S plane, and this is real S, and this imaginary of S. Basically, we can write is sigma plus j omega. So sigma is the real part, and this is the imaginary part, which moves along the imaginary axis. Now, the location of the poles, if the poles of the systems are lies on the right hand side, the systems assumed to be unstable. If all poles are lies on the left hand side, left hand plane, then we can say the system is stable. So we can write this is the unstable region, and this is the stable region. So for the stable system, all poles should be lie on the left hand plane. And for the unstable system, if any of the poles comes out to be in the right hand side, the system will be unstable. Let's assume another plot. This is RE of S, this is IM of S. If the poles lies on the right hand side on the real axis, the response will be divergent, something like this. If the poles lies on the left hand side negative real axis, I can say the response will be converging to the or exponentially stable system, we can say. If the poles comes out to be complex conjugate in right half plane, the system will diverging with oscillations. So it may start like this, it may diverge like this. And if the poles are lies on the left hand side, left hand plant in stable region with complex conjugate poles, the response will be converging to the equilibrium point or the desired value. So it may start like this, something like this. It will go decaying oscillation. So from this, we can write this part. If the pole going in this direction from the imaginary axis, so we can say oscillation increasing growth if they are complex conjugate. And if the poles goes in this direction, and the response can be oscillations decaying, actually, because if the poles are here, for example, so of course this negative real part will be higher than this side. So if the negative real part is increasing, the speed of decreasing the oscillation will be reduced very fast. And if it is found to be the poles lies on the origin, if there's a single pole at the origin s equal to 0, for example, and here the system response will be something like this, marginally stable. So this kind of response marginally stable. And if it is found to be there are two repeated poles at the origin, then system response will be unstable. So it is something like this. So this is how the response yields based on the location of the poles in the S-plane. So this is very, very important concept. And based on the location of the poles, we can design the control. If it is found to be all the poles or one of the poles lies on the right hand side, with the application of the control algorithm, we can make that system stable in closed loop. So in open loop, if it is found to be the poles are lies right hand side, with the application of control, we can come up with the closed loop control system, and we can comment on the stability of the system. So we can make the system stable if we add some poles and zeros to the system. So this is how we design the control, how we can add the poles using the application of the control. So let me draw it. Suppose we have system This is our plant, GP office, and this plant is affected by U office some control, and this is our control algorithm or control transfer function, we can say. So actually, if it is found to be the plant is unstable, we can add some pole and zeros to the system. We can make the system closed loop system can be stable. We can make. So if GPS is found to be unstable, means if any of the poles lies on the right hand side, system is unstable, then with the control law can add poles or zeros to the system which makes unstable system to stable. So this is how we design the control algorithm. We'll be doing all these things later also, how we can come up with some examples and how we can make the unstable system to stable using the control. We'll be doing the another part of transient response. So before we had this part already, but I want to revise. So we have some response y of t and versus t. Suppose this is the signal, the desired signal, for example, y final to be tracked, and my system starting from 0 and going like this. So now, before it goes to steady state value, we call the response transient response. And after it reaches to the steady state, and after onwards, after it reaches steady state, the rest of the part we call steady state response. Now, as of now, we have discussed how we can modify this transient response using the time domain specification TR, TP, MP, and TS, settling time. So this part we can modify the transient response part using the rise time, settling time, peak time, and maximum overshoot. Now, what about the steady state part? How we can modify? Because in steady state, the system can have some error. Practically, there can be some error in the system. This may desired values, and suppose there are some error in the system. So how we can modify this steady state error using some control or any other way, adding some poles and zeros? How can we modify it? This is the part of starting now. So the title is Steady State Specifications. So here we'll come up with some specification as we have done for transient response to modify the steady state response in the system. Let me draw the closed loop system, closed loop diagram. This figure is very important in control system. This is the way the autopilot being designed. This is my RS, and we have controller GC office, and We have not used in the previous cases that disturbance, but there are continuous disturbance may act in the system practically, which makes the problem of a steady state error in the system. This is the output from the summing point, and this is our GP of S, and this is the plant output Y of S, and this is another summing point where noise is acting, and this is unit feedback plus plus, this negative, this plus, this plus, this plus. And as a control engineer, we always want the Y of S to track R of S. So always objective is, as a control engineer, we always want E of t equal to R of t minus Y of t should go to 0. But in practically, this cannot be possible because of in practical, there are some disturbance. If you consider the aircraft system, there are some always continuous disturbance acting on the system, maybe wind disturbance, maybe due to the engine, due to some unmodeled dynamics in the system. This part is difficult to achieve, this errors to 0. And so due to this problem, how we can modify the steady state error in the system. We can't make it to equal to 0, but to some extent, how can modify? But in practically not possible, but still we can come up with some specification which will help us to modify this steady state error. So let's have the closed loop system corresponding to WS equal to 0. Since WS is the part of the frequency analysis, so we'll be dealing with later. Now let's constraint with disturbance and reference signal. The closed loop system corresponding to WS equal to 0, we can write Y of S. This is already have done how we derived it, so we are not considering the WS part. GP of S, GC of S, 1 plus GP of S, GC of S, RS plus GP of S, 1 plus GP of S, GC of S, MDS. So we are assuming the reference inputs RS and the disturbance MDS for the time being. An error we can find E of S, we can write RS minus YS. Or we can further write RS minus, in place of GPS, if we substitute this expression, let me define this equation number 1. So if we substitute equation number 1 in place of YS, we'll have GP of S, GC of S, 1 plus GP of S, GC of S, RS minus GP of S, 1 plus GP of S, GC of S, MDS. Or we can write further, if you combine these two terms, we can get 1 by 1 plus GP of S, GC of S, RS minus GP of S, 1 plus GP of S, GC of S, MDS. We'll first consider this term and then we'll study on this term. Here, if you notice, RS is the test signal or the reference signal we have used. But in practically, this RS may not be constant or 1 by S, or we can write R of t equal to 1. But this reference signal may not be constant in some cases, which we would like to track. We may or may not know in advance what RT is going to be. And even if you do know it, it may not have simple form that is useful for control design. So therefore, we'll examine now the closed loop system response to test signal, which are similar to the expected reference signal RT. So there are some other standard reference signal we can use. Let me start with the step input. So where these reference signal are useful when R of t equal to 1 and R of s equal to 1 upon s. And the response, as we have done before, this is our response, R of t, this is t, and this is basically 1. So R of t equal to 1 when t is greater than equal to 0. And equal to 0 is t is less than 0. This is the condition for step signal, right? This is the appropriate when the reference signal RT is approximately constant for long period of time. So for example, we want to occasionally change the attitude from one fixed reference attitude to another. So when this kind of situation arises, we can use this step signal. Suppose we want to give the R of t equal to 60 degree, for example. And in next case, if you want to 70 degree, some constant value we want to apply to the system as a reference signal. So in those cases, we can use our step input as a reference signal. Now there's another signal we can use, ramp input. So ramp input we denote by R of t equal to t and R of s equal to 1 upon s squared. And if you see in response of R of t, it's look like this. So this is appropriate when the reference signal R of t is slowly varying. This can be used when the reference signal R of t is slowly varying. Why you are talking this type of signal will come very soon. Why the reason behind it? Because R of t equal to 1, this is already we have done. Why? This is the step response for this, for when we are using R of t equal to 1. So when you are using R of t equal to t, this is basically ramp response, how the system response going to be this ramp input. And so in this case, if you want to, when you have to use this ramp input, we want to want the aircraft to perform a slow attitude maneuver. So when we need the slow maneuver of the orientation of the aircraft, we can use RT equal to T, ramp input. There are another reference signal we can generally use. I should not say generally use, we don't use very often actually. Acceleration input. R of t equal to t squared by 2. or R of S equal to 1 upon S cube. And the figure for this response, we can write something like this. This is R of t, this is t versus. So this acceleration input signal generally not commonly used. So in most of the autopilot, we generally use steps input or ramp input for designing the autopilot. But step input very common, and we can test the system or controller, closed loop control system, whether it is perfectly working or not. But ramp input, when we need the slowly varying aircraft, that in that case we can use this R of t equal to t ramp input. Now we'd like to discuss more on the this part. How we can this, let me write this the equation number 2. So using these signals, step input, ramp input, or acceleration input, how we can modify the system response in steady state? How we can modify in steady state part? How we can modify? This is the objective. Before we move to that part, let me discuss on the type of the system, because this is very important. How we can define the type of the system. Based on the type of the system, we can choose what kind of test signal we should refer as a reference input for the controller design. We'll be using this first term since we are going to work on the reference signal. So this part we'll be taking later. So for the time being, we'll consider, if you ignore MD is equal to 0 from equation 2, we can write E of S equal to 1 by 1 plus GP of S, GC of S into RS. Or we can write 1 by 1 plus G naught S RS. This is very, very important. So here, G naught is called open loop transfer function. So how can define this for us in the closed loop system? Suppose we have, this is my summing point. This is the controller block, CC office, and this is my plant GP office, and this is, let's assume one sensor is here, which transfer function H is. In the earlier cases, we assume Hs should be 1, but if there is Hs, the sensor transfer function is there, then how we can define the open loop transfer function? This is R of S, this is Y of S. Now, the open loop transfer function, let me define, then I'll explain. The open loop transfer function to be the product of all transfer function around the loop. So in this case, in this figure, that open loop transfer function, we can write GC of S, GP of S, HF of S. This is the open loop transfer function. And if you assume, if we consider Hs as a unity feedback system equal to 1, then OLTF or G naught S will be simple GC of S, GP of S. So this is what we have done here. This is our G naught S, which is GP of S, GC of S. For this case, we have assumed the sensor transfer function is 1. So that's why it is like that. Now, in general, the OLTF can be written as G naught S equal to K bar S minus Z1 S minus Zm S to the power n S minus P1 S minus Pn. So where Zi zeros and Pi poles. So this open loop transfer function is written in terms of poles and zeros. So and this is the gain which is coming from the transfer function. We'll discuss later while we'll be taking the example, you'll understand. So here, based on this number of poles at or because this indicates S equal to 0, right? If it is 1S is equal to 0 and other poles, some numerical value is there, but for this part, basically S equal to 0, it indicates number of poles at origin actually describe or classify the type of the system. Which type of the system? So based on the number of the poles at origin, we define the what type of system. If there is only one S, then type 0 system at origin, then if it is S only, it means n equal to 1, then type 1 system. And if it is S to the 0, it is type 0 system. Type 0 system. If S squared, then type 2 system. So if there is no poles, for example, at origin, then S to the n will be 1 because n equal to 0, then S to the n will be 1. So this is how we define the type of the system. Let's stop it here. We'll continue from the next lecture how we can come up with some steady state specification which will help us to modify the steady state behavior of the system. Thank you.